My name is Richard Hoover. I thought I'd like to talk today about some of my early experiences at the NASA Marshall Space Flight Center. I joined NASA in February of 1966 and came to the Astronautics Laboratory of the Marshall Space Flight Center in the Applied Research Division. My first laboratory director was Dr. Walter Koiserman. He was one of the original Peenemünde team members who came here with Dr. Werner von Braun when the people from Peenemünde were surrendered to the Americans and came to work on rocketry out at White Sands Missile Range, which at that time was called the Army Proving Grounds. And Dr. von Braun brought with him a number of scientists and engineers, about 125. And after they had been there a few years, the Redstone Arsenal was established, and they came here to work at the U.S. Army Missile Command on the development of the Redstone rocket, which launched our first satellite, the Explorer 1. When I came to NASA, we were just finishing the Gemini program. The Mercury had already completed, and there was a great deal of work going on the development of the Saturn system of vehicles, the Saturn 1, the Saturn 1D, and the Saturn 5, which we have here in the Davidson Center, and that was used to launch the missions to the moon. I'm sitting in front of the Apollo 16 command module, which flew to the moon in 1972 and was piloted by Mattingly, Duke, and Young. In 1972, the mission was, from the beginning, was a tremendous success. My first work at the NASA Marshall Space Flight Center was in developing a telescope to be used for checking the technology that was initially planned for laser tracking, communication, and guidance of the Saturn V vehicles on the way to the moon. This was to put optical corner cube reflectors on the service module, and then to illuminate the Saturn V vehicle on the way to the moon with laser beams, and by seeing the direction that the telescope was pointing and measuring the exact time from the pulse going to the Saturn V vehicle and returning. Since you know the speed of light extremely accurately, you could tell precisely how far away it was from the Earth. One of the fundamental problems was we needed to be able to show that this concept would actually work. And so we built optical corner cube reflectors, which are like the corner of a box, but made out of a very high quality glass that is very highly polished. And if you shine a laser beam into the square base of this pyramid, when it hits one of the triangular faces, it reflects to the opposite triangular face, and then in return directly back through the base in the precise direction that it came from. So you send out a pulse of light from the telescope, and it goes to the corner reflector, and then it returns back to the same telescope that sent it. And that technology had been actually proposed in the early 1960s in order to try to measure the precise distance to the moon, so that it would be possible to test the theories of gravitation and so forth by Professor Dickey and others at the University of Maryland. They had tried this by shining lasers, sending laser beams directly to the moon and having them return, but they could only determine the distance from the Earth to the moon to a precision of about a mile. They wanted much better than that. So we worked on testing the concept by actually putting optical corner cube reflectors on the A-12 Oxcart and on the U-2 aircraft that were flown over Huntsville, and we ultimately were successful in acquiring the retroreflector. If we knew exactly where the where the aircraft was going to be and tracking it for a short distance of time as it traveled across Huntsville. The first job that we had was proving that this technology would work, and we needed an extremely high quality telescope, and my initial activity was to determine how this telescope could be tested. And so I had to calculate, since we wanted it to be a diffraction limited telescope, what kind of mirrors would be needed, and found out originally that it was going to require a hyperboloid of 1/100th of a wave for the primary and 100th wave secondary, and it was going to require 125th wave folding flats. Well, no one on Earth could build that, and so we had to revise the specifications, and ultimately we got a superb telescope built and deployed on Madkin Mountain, and we're able to use it to verify proof of concept. Ultimately, the plan to put retroreflectors on the service module for Apollo 8 was not possible because everything that was not essential had to be removed because of weight, so the corner reflectors were not flown on the Apollo 8 mission. But then Professor Dickey persuaded NASA to fly an array of these corner reflectors on Apollo 11. And laser beams were sent out from the McDonald Observatory and the Lick Observatory, and they succeeded in acquiring the corner reflector array for the on the surface of the moon, and that made it possible to determine the distance from the Earth to the moon, from the telescope to the moon, to a precision of only a few inches. Later, on Apollo 15, a bigger array was deployed at the Apache Point Optical Lunar Laser Observatory, named Apollo, and that made it possible to determine the distance to a precision of about plus or minus a millimeter. With that kind of accuracy, it was possible to get a precise calculation of the universal constant of gravitation, big G, and in that way understand the nature of gravitation far more precisely, and show that general relativity was actually a more precise representation than string theory. During that program, I had the opportunity to meet and work with many, many wonderful and brilliant people. My first laboratory director at NASA Marshall Space Flight Center was Walter Heusermann. My first center director was Dr. Werner von Braun. And I was in the applied research division under James C. Taylor. When we started working this project, it became immediately obvious that we were going to have someone who was tremendously capable in fabricating fine optics, and the initial job of making the first prototype mirrors was done in the optical laboratory in the Astronautics Laboratory at Marshall Space Flight Center, but then a contract was awarded to Perkin-Elmer, and they made the array of small corner cube reflectors that were flown to the moon by the Apollo 11 astronauts. Buzz Aldrin actually, on the 21st of July in 1969, pointed this array toward the Earth, and so the original beam coming out of the telescope, by the time it reached the moon, it was about a mile in diameter, and by the time it returned, it was about 5 miles in diameter, so it was not terribly difficult, although it did take until the 1st of August before they actually were successful in getting a return beam. It was thought that the LRRR, the Lunar Laser Ranging Retroreflector, would function for about a year, and then it would be covered by lunar dust and cease to work. Well, it turns out that was incorrect because lasers became more powerful and the dust particles were spread out, and so even though you lost some of the area that was capable of reflecting the beam back to Earth, you now had a much brighter source, and you had much finer pulses. And so the LRR experiment that was carried to the moon by the Apollo 11 astronauts is the only lunar experiment that is continuing to function and provide data to this very day. After my work on the Lunar Laser Retroreflector Array in 1968, the Marshall Space Flight Center started working on the Apollo telescope mount that was to be flown on the Skylab, our first orbiting observatory. We have the Skylab trainer sitting right down here, and it was used by all of the Skylab astronauts during their training. In fact, when Jack Lousma and Ed Gibson came here a few years ago, I was with them as they walked into the door of the Skylab trainer, and it was intriguing because they both said the same thing simultaneously. They said, home. They had lived there and worked there during all this period of time, and it was so wonderful to see them come back and explain to us exactly how the shower Skylab worked, exactly how the various experiments worked, and we could see into the area where they were controlling, the scientists were controlling the Apollo telescope mount, which carried an array of telescopes to look at the sun at many different wavelengths. And my job was in the design and development of the Apollo telescope mount experiment SO56. As co-investigator with James H. Underwood and James E. Milligan, I worked on the optical system, which was called the Wolter 1 X-ray telescope. It was a glancing incident paraboloid hyperboloid mirror system, and that took X-rays and from the sun and focused them onto photographic film, and we were able to achieve arc-second spatial resolution with the instrument. This produced about 25,000 X-ray pictures of the sun, which made it possible to learn a great deal about active regions, about coronal holes, about all sorts of phenomena, solar flares and so forth, that had never before been possible to be seen simultaneously in hydrogen alpha and the calcium K line, and with a white light coronagraph, and with the two X-ray telescopes that were flown on Skylab. One was the Marshall Space Flight Center ATM experiment SO56, and the other was the American Science and Engineering Telescope ATM experiment SO54, and the principal investigator of SO54 was Nobel Prize winner Riccardo Giacconi. So during the work on these programs, I had a wonderful opportunity to meet and work with many very, very brilliant scientists that were at the very beginnings of the development of X-ray optical systems and of X-ray astronomy. Actually, X-ray astronomy came about as a serendipitous event. Riccardo Giacconi had wanted to learn more in the very early days about the composition of the moon, because no one really knew what was the chemical composition of the moon, what was the nature of lunar dust, and so forth. And he persuaded NASA to allow him to fly a telescope on a sounding rocket. Well, actually, it was not a telescope, but an instrument for detecting X-rays from the moon that would have been produced by the solar wind striking the moon and exciting the atoms in the rocks and dust of the moon and producing X-rays. And his concept then was to look at these X-rays to try to determine the composition of the lunar dust. So he flew this experiment, and as it scanned past the moon, it was a total failure because it received no X-rays at all from the moon. But as they analyzed the data, they saw a very sharp blip as it went past the moon. And actually, by total chance, the moon happened to be in the right place, so that when they went past the moon, they scanned past Scorpius X1, which was the brightest X-ray source in the entire sky. And so they discovered an X-ray star, and that gave birth to the whole field of X-ray astronomy. At that point in time, people like Dr. James H. Underwood and Stu Boyer and others started to fly instruments. Stu Boyer's instrument was flown and actually in planning at about the same time that Giacconi announced his results of the discovery of the first X-ray star known to man. And so shortly after that, Stu Boyer obtained data from the Crab Nebula, which was a supernova that exploded in 1054 AD. We know that because of Chinese records. We know that because actually there are drawings on cave walls showing the representation of the Crab supernova explosion. So we then started the testing of the X-ray telescope that was fabricated. We made 3 fused silica telescope mirrors at Perkin-Elmer, and we made 3 Canadian-coated beryllium X-ray telescope mirrors. So those tests were carried out at the Martin Marietta facility. I spent many months going back and forth from Huntsville to Boulder, Colorado, and to the Martin facility just outside of Denver, and working in their 100-foot vacuum chamber that was capable of allowing X-rays to be sent for a relatively long distance, not nearly as long as we wanted, but then we built a much better chamber here at Marshall that was used later for testing some of my other X-ray experiments. I worked on several different kinds of X-ray optical systems and received many different patents on the extended range X-ray telescope and various others. So after the work was done on X-ray astronomy, the experiments were flown, I started working closely with Professor Sir Robert L.F. Boyd, the director of the Mullard Space Science Laboratory in England, Holmbury St. Mary, Dr. Ian Toohey, Lynn Culhane, Pete Sanford. These were all pioneers in the field of X-ray astronomy, and we worked on the development of a telescope that we flew from South Australia to look at the Papaseis supernova remnant. That was a wonderful time in South Australia. I spent a fair bit of time in the desert on the Woomera rocket range preparing the telescope. A number of very strange things happened. One day I was suiting up to go in the clean room, and I heard this crunch, crackle, pop, and I looked down, and as I jumped back, there was a long creature there, about 8 inches long and 1.5 inches in diameter, jet black with yellow legs and yellow, red, orange antenna. And as it started scurrying away, I grabbed a coffee can and put it down over it and ultimately scooped it up into the coffee can and carried it into the laboratory where the naturalist John Eiston worked. And John looked at it and he said, "My God," he said, "where did you get that?" And I said, "In the clean room." He said, "The clean room?" I said, "Yes." He said, "And how did you catch it?" I said, "Well, I stepped on it and it started running away." Oh, he said, "You're lucky about that." I said, "Why?" He said, "Well, that's one of our rather nasty centipedes." And he said, "The problem is when they get frightened, they always have a tendency to try to run to the highest object around, and sometimes that's a person. And the problem is, if it runs up your leg, everywhere that those legs touch your skin, and they can go through clothing, it causes the tissue to die. So you get a lot of little places where the venom has caused the skin, the tissue to die, and chunks of tissue actually come out. So you wind up with holes and scars, and it's incredibly painful. So he said you were lucky that he didn't decide to run up you rather than try to run away. Anyhow, we discussed this, and he said, I think what we should do is make a souvenir for you out of it. And I said, a souvenir? He said, yeah. He said, let's pot it in a potting compound that I have. I said, oh, that's wonderful. So we took the can and centipede and stuck it in the freezer, and put liquid nitrogen in with it, and so we cooled it down to liquid nitrogen temperature, and went on working on the alignment of the telescope in preparation for the launch from the Woomera rocket range. And about 5 days later, I was in there with John again, and he said, let's go fix your centipede. So we went and got it out of the freezer, and he dumped it out on the workbench, and he's mixing up this potting compound that he was going to put it in so it would be a nice big object you could put on your coffee table. And all of a sudden I yelled, John, watch out, because this creature had thawed out and started crawling toward him. He reached over and picked up a big hammer and goes bam like that, and smashed it in the head and kept it from attacking him. But unfortunately, I lost my souvenir as well. So strange things happen. We also, another interesting thing that occurred was we were testing the X-ray telescope out at Martin Marietta. There was a guy out there with the name of Ed Dingman who had a brilliant guy. Ed was. He slept very little. He read almost all night long. He would sleep only 3 or 4 hours a night, because Ed had been injured during the Manhattan Project. They were working on some configurations, and they had these bricks that simulated the radioactive material, and they were in a room, and there were 3 failures simultaneously. One, the bricks were supposed to be painted red if they were live, and painted green if they were dummies. And it turns out that these were live, that had somehow been painted the wrong color. And when they picked one of them up and found it was warm to the touch, they immediately left. There were 4 people in the room, 3 of them died, and Dingman survived, although he was in the hospital for many months being treated for radiation exposure. And this caused him to have all sorts of requirements for calcium and other injections routinely. But Dingman was also a hiker, and he would go out on the outbacks and he would collect rattlesnakes. So he carried with him a snake loop, and one day he came back with about a 6-foot diamondback and walked into the laboratory with it wriggling with its loop around the neck or the head of this diamondback, and walked over. We had a big cooler with liquid nitrogen, and when he put the snake near the liquid nitrogen, it started writhing around, and he then stuck it down into the nitrogen and held it under the liquid nitrogen for about 2 minutes. And when he pulled it out, it was frozen solid, but all coiled and curving. and he has his heavy gloves on, and he was holding it by its tail. And the lab director, Bob Riston, walked into the lab, and Ed swung around and says, "Hey Bob, look at this." And as he swung his arm around, there was a slight tink as the end of the tail of the snake broke, and it goes swirling through the air toward Bob Riston, who immediately jumped back. It missed him by only a matter of inches, and as it came down on the concrete floor, it was like fine crystal as it shattered, and pieces of rattlesnake went sliding across the floor. and then to thaw out and start bleeding all over in tiny little spots everywhere that chunks of rattlesnake had landed. And Bob looked at Dingman, still white, and he said, "Ed, clean this mess up and see me in my office in 5 minutes." He was not amused. Funny thing happened on the way to the sun and to the moon. Many, many interesting and unusual occurrences took place, and I had such a wonderful time getting to work for and meet so many fabulous people. After I left Astronautics Laboratory, I went to the Space Science Laboratory, and my director there was Gerhard Heller. Gerhard Heller had worked for Wernher von Braun at Peenemünde, and actually he was in charge of the development of hypergolic rocket fuels. And Magnus, Wernher von Braun's brother, went to work for Gerhard Heller because Magnus von Braun was a chemist, and Magnus helped develop the rocket fuels that were flown on the V2 rockets, and learned a great deal about not only hypergolic fuels, but a variety of other fuels that were used for the V2 and ultimately came to be used in the American space program. So that's sort of a resume of some of my early days at NASA Marshall Space Flight Center, and having a chance to work with so many brilliant and wonderful scientists and engineers that were at the very beginnings of the American space program. And I thank you, and I will discuss other details at a future date. Thank you very much.